Okay, let's get started. So today we will start looking at what is known as finite state Markov chains. Maybe I'll start with a simple example. Okay, so in this case, all the random variables are discrete. Okay, so I'm not going to talk about continuous time Markov chains or all the random variables involved are discrete, and there is the notion of state. Even the state is finite. Okay, so let's look at this. Okay, so let's look at a random walk. So what is a random walk in one dimension? So this is your 0, 1, 2 and 3, -1, -2 and -3. Okay, so person starting from here, let's say he's going to take a step right or left with certain probability. Okay, and then again the moment he suppose he's going to toss a coin with certain the bias. If it is head, he's going to move right or to the left. Okay, so that's what he's going to do. So by the time he, supposing let's say he reaches, let's say this state, then he's going to move to, let's say, 2 with probability. Suppose again he's going to toss the same coin. He's going to move to the state or the position 2 if it is head. Otherwise he's going to move to state -3 or the position -3. Okay, likewise here. So if it is a head, he'll move to 2 -2. Otherwise he'll move to 3. Is that fine?
Yes, sir.
Okay, so
So
now
that means it stays.
huh?
That means that's the limit -3 and 3. It cannot cross
Yeah, it
that.
cannot cross. Okay, I'm just looking at a finite state Markov chain because there is this notion of state. State corresponds to positions. Finite means there are finitely many positions. I'll talk about what Markov chains are. Okay, so now I'll denote this state by -3, -2, etc. 2, 3. Okay, these things. These are states. It's finite. Okay, and there's random variable. For example, x0 denotes the position of the person at time 0. So this will be 0 with probability 1. Okay, for sure assume that there is a bar or something and he's doing a random walk. So he's going to start at 0 with probability 1.
Sir,
Yes,
so is it necessary to have a symmetric around zero, sir, like
not
+3 and
necessary. No, no,
no
no,
necessary, no, sir? Yeah.
not necessary. Okay,
Okay.
okay, okay. So let's assume that x1, okay, is going to be +1 with probability, let's say I'll make this simple. So p01 -1 with probability p0 -1. Okay, x2 is again, so basically okay, so let me make it very simple only. So I'll just use p minus p. Okay, so this is true only when I'll make it general xn nth
So
step.
always
Plus,
it
sir,
can be
Yes.
negative.
Hmm?
that should be 1 minus p, right?
Huh?
Sir, that should be 1 minus p. Second one.
This is 1 minus p. Yes, you are right. Good. So only when xn not equal to -3 or 3. Okay. If xn is equal to 3, sorry, xn -1. Okay, the previous one. I don't. What am I doing? No, no, no. Wait. Okay, so I'm sorry. Okay, let me use a different random variable. Okay, y0. Y0 is the position. Xn is some random variable. Okay, so I'll define yn -1, the previous state in which the person is in. If it is not -3 or 3, then xn is +1 -1. Okay, if yn -1 is equal to 3, okay, xn will be what? What will be xn? It will be
Only
minus 4 with probability p, or minus 1 with probability 1 minus p, right? If yn is minus 3, you can fill the gap. Okay, so this now what will happen? So what is yn actually? Yn
Hello,
is
hello, sir.
yn minus 1
Sir,
plus xn. Yes,
Hello.
yes,
it
yes,
is a
yes.
-3, I think, no, sir, in place of -4 because it is a.
Hmm?
So it will be -3, I think, no, sir.
Which one?
Sir,
Oh,
three
sorry.
only, I
exponential.
think it's
If it is 3, it should go to, if I add minus 1 to it, you go to 2 with probability 1 minus p, or you will go to minus 3. So it should be minus 6. Is this fine?
Sir, you said it will stay at that.
Okay, whatever. So, okay, so I'll slightly change. So you go to 2 or minus 3. Okay, it doesn't change the whole thing much. Is this fine, Rishabh? You can either stay or you can define it to go to 0 or 1 or whatever. Okay,
Okay, well, I mean
right?
deterministic. That deterministic.
It's not deterministic. It's with certain probability that happens. With certain probability, you
Look,
stay,
the
otherwise
state
move on.
that I'm going, that is fixed from before
Hmm?
the experiment. I mean, the state that I will be going
Hmm.
after reaching the limit, that is deterministic. With probability, I mean, the states are defined. I mean,
No, the states are fixed, minus 3 to 3. In which state are you in after n step is random, right? You don't know. It depends on what will be the outcome of the coin, right? Do you agree?
Hello, sir.
Yes, Ayush.
Sir, here the xn you have written in this page only.
Hmm.
Plus
Mhm.
1 when probability is 1. P and minus 1 where
Correct.
when 1 minus p. So, sir, plus 1 with respect to previous step.
No, no, no. It doesn't matter. If I'm going to take a coin with bias P, toss it. If it is head, it will be plus 1. It's tail, minus 1. That's all.
So, plus 1 is the location where it is on the number line.
No, 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 no. So xn is something else, okay? The position is this yn. That's why I changed the notation, right? Y0 is 0. You start at 0 with probability 1. Okay, that will be your position at time 0. At time 1, what will be the position? You can calculate from this, right? Yn, y1 is y0 plus x1. Y0 is 0, so it will be x1. So, for example, x1 is 1, then you go to 1 from 0. If it is minus 1, you go to minus 1. Okay, what will happen subsequently? You will add or subtract to the current position with certain probability. If you are in 3 or minus 3, then the one that you subtract or add will be different. It will be minus 6 and minus 1. Is that fine?
So, how did we get this minus 6 and minus 1? Can you explain once again?
For example, if you are in 3, right? Okay. With probability, let's say it goes to 2 with probability p, or it goes to minus 3 with probability 1 minus p. That's the definition. That's how I have constructed my chain. Okay. If you're not happy with that, you can say, well, you go to 2 or 1 or 2, or you stay back, whatever you can define.
Okay, so the xn is defined by us here. So, it is not
Yes, yes.
being calculated.
No, no, no. So everything is defined. Nothing is calculated now. So I'm going to define. If you're not happy, you can just say with probability P, if you are in state 3, with probability P, you go to state 2, or you stay with probability 1 minus P, you stay in state 3. That is also a valid Markov chain. Okay, whatever
Okay,
Markov chain
okay.
means. Okay. Now what you can see here is this xns are IID. Okay. So these are all not IID, independent. Because the way I'm going to toss the coin, they're all independent. Okay, so now with this, what can you say about xn? This is a stochastic process, right? N equal to, so not xn, n equal to 0, 1, 2, etc. This is a stochastic process. It's a discrete stochastic process because n is discrete, as well as yn also takes finite values, right? Is this fine? So what is it that you can say about this yn? See, yn given yn minus 1. So the future state in which you will be in, the immediate future state that you will be in, is independent of all the past given the current, right? For example, if you are here, right, the future state. So suppose I come here, right? The probability or the chances that I come here, given the previous states, it depends only on the immediate previous, right? Because I cannot come. You understand what I'm saying? Hmm? So what I'm saying is probability of yn equal to some state in, given yn minus 1 I was in some state in minus 1, yn minus 2 I was in some state in minus 2, etc. y1 I was in state I1, because y0 is anyway 0 with probability 1, so I need not even condition on that. This chance, right, depends only on the immediate neighbor.
Hello, sir.
Yes.
Sir, is it also true for the extreme case, like when after yn equal to 3, I go to minus 6? This can also happen if I am in minus 2 position and I get a tail. I go to minus.
Yes. It's possible. So what I am saying is the chances depend only on the previous state. It doesn't depend on all the previous. Okay.
Okay.
So it doesn't matter which path you took to come there. It depends only on what is it that you were in the previous state, previous time slot. That's all. Is this clear?
Yes, sir.
Intuitively clear. I mean, we can rigorously show this, but is this clear?
Yes, sir.
Yeah. Okay. Actually, this follows from definition, right? So what is yn? I can write this, right? Yn is yn minus 1 plus xn, right? So yn minus 1 is conditioned on in minus 1. So it becomes xn is equal to in minus 1, right? So xn is independent of all yn minus 2, yn minus 3 by construction or by definition. So it depends only on. So okay, let me write this. Okay, this is how you generally prove. What is yn? Yn minus 1 plus xn is in, given all this, right? So this is equal to, so there is a yn minus 1 equal to in minus 1, right? So since I'm conditioning on this, this will be in minus 1 given all these, right? So now by definition, this is nothing but xn equal to in minus 1, because it doesn't depend on anything else, right? Because xn is independent of everything. But this I can write it as probability of xn equal to in minus 1 given yn minus 1 equal to in minus 1. Because xn is independent of yn minus 1, conditioning doesn't change, right? So both are equal. So what can I say about this? I can say in minus 1 is yn minus 1. So I can say yn minus 1 plus xn is equal to in given in minus 1 equal to in minus 1, right? This is nothing but probability of yn equal to in given yn minus 1 equal to in minus 1, right? This is the computation. So essentially what I have shown is conditioning on everything depends only on the immediate past. I have actually proved it. Now, is this clear? Okay. Shall we define what a discrete time Markov chain is?